Hello my friends. We recently had a power outage. It lasted about 5 hours and that was enough time for me to lose about 200 of my tilapia, the smaller ones, and a couple large ones. So that got me wanting to make a backup. I had it planned for a while, but I didn't get it in. I guess it takes a power outage and fish loss to make you go ahead and do this. So this is what I come up with, and it works really well. I'm using a Hydrocyclone Aeration system, and it's based around the relay. It's a double pull, double throw relay that operates off of 110 volts. So when you lose your power, you lose energy to the relay, and when that happens, it closes some contacts, which turns the pump on and circulates the water in the system. So here I have a schematic of the electrical system driving the relay. So right here, this block right here is the relay. It's a 110 volt relay. This is the coil in the relay, and it's plugged into 110. Okay, the relay that I purchased has two sets of contacts, and a single set of contacts, which would be the top section there, would be a single pull and a double throw. So it's going to be in an on position or an off position. Well, this has two sets in there, and I connected the two sets together. The contacts are rated at 5 amps of current carrying capacity. So by connecting the two together, that allows me to carry 10 amps through my circuit. Okay, the bilge pump that it's driving is a small bilge pump. It's 12 volts and it's made by Rule. So when you lose power, the relay will switch back to a normally closed position. It's driven by a 12 volt battery. That battery has to be maintained at the 12 volts or it's not going to be effective when you lose power. So to keep this battery charged, you have to keep it on a small trickle charger, and that'll keep the battery topped up. Now that battery should run that pump for quite some time. The pump is drawing 1.9 amps, and when I have the system finished, I'll be running 4 pumps. So that should be about 8 amps that it'll be drawing. Now the batteries are usually rated in ampere hours, and that could give you an idea of how long the system will be running those pumps until the batteries completely wore out. But it should be long enough that the power will come back on. So typically a deep cycle battery is going to be running between 800 and 1000 ampere hours. So at that rate, at 8 amps, that should give you a minimum of about 10 hours of operating time before it's completely discharged. And even then, when it's starting to lose its charge, it's going to slow up its pumping action, and it'll probably extend, but it won't be quite as efficient. But 10 hours should be more than enough to get that power turned back on. What I did is I used a 5-gallon bucket, and in the dead center of the bottom of the bucket, I drilled a 1.5 inch hole. And I used a vinyl hose, 3-foot length of vinyl hose, comes up, and I have it zip tied to the top end of the bucket, and it's coming in tangent to the top of the bucket, and it will cause a swirling action as it's coming in. That swirling action is going to cause a whirlpool, and that will be aerating the water as it's doing that. The pump is then submersed roughly about 1 foot under the bottom of the surface of the water. And I did not want to go down to the bottom of the tank. I don't want the pump to be picking up any solids. So I'm keeping it in the upper half of the fish tanks just to have less chance of picking up solids. Now this bilge pump that I have, I can't remember the price, but I think it was around $19 or so. It was pretty cheap. The specs on this particular pump, I'm running it horizontally like this because of the outflow, and it's a 3/4 inch barb fitting. So this is coming straight up into my tank. But the pump itself, it's a model 25D, it's a 12-volt pump. It pumps 500 gallons per hour. And my tanks are 250 gallons. So that's going to, in a half hour, it's going to circulate the entire volume of that tank. So that's a pretty good flow rate. So there shouldn't be any issue with that water not being aerated. And of course the draw that the pump is taking is 1.9 amp at 12 volts. By trial and error, I found that an 1.5 inch diameter hole is the exact size needed in the bottom of this 5-gallon bucket. 2 1/4 inch holes are being drilled near the top edge of the bucket. This is to use a zip tie to hold the 3/4 inch vinyl hose. Here I'm prepping the lead wire that's going to connect to my bilge pump. See here, this is speaker wire. It's 14 gauge, and one side will be marked. This has a white line, so that's color coded. I'm going to use white as a ground. Also, I'm going to use black as a ground. So I'm going to make my connections, and I'm going to solder them. This is a Rule pump. It has 500 gallons per hour. For such a small pump, it really delivers. And black is the ground, so we're going to connect the black and the white together. And you make a mechanical joint first. So a mechanical joint means it could just be twisted. And I also want heat shrink, so I need to get a piece of heat shrink. Here's heat shrink. Heat shrink typically shrinks a 2-to-1, so you need to have a fairly close fit before you put it on the wire. When you're soldering, you need to use a solder that has a rosin core. If it's an acid core for wiring, it will corrode the wire. It can ruin electrical connections. Okay, you apply the heat to the underside, and you apply the solder to the top, and the wicking action will make it flow. And it flows towards the heat. Okay, now this is beeswax, and to make a watertight fit, I apply beeswax to this, and I'm going to put some beeswax inside the heat shrink. So I'll take some slivers and put that in there. There. It's warming it up so I can apply pieces to it. Some heat shrink comes with beeswax already on the inside of the tubing, and when you heat it up it will melt the beeswax and you'll actually see some of it flowing from outside of the tube. So this should do the same thing. See right there, I got a ball around it. There is a chance that these could get wet, so that's why I'm doing the extra precaution. There it is, right over the middle. Okay, my heat gun. Right there, see the beeswax melted and oozed out. So that should be a watertight electrical connection. This is going to be the bus bar for the electrical connection. I'm going to use one half for the plus, the other half for the minus. So I need to daisy link 4 of these together so that I'll have 4 terminals for each tank. This end of the pump will be the vinyl hose. The vinyl with the cloth inside is food grade, and it's a 3/4 inch barb fitting, and I have a stainless steel hose clamp. When you're fastening hose clamps, you should be using this type of a screwdriver. The hose clamp comes with a hex head, and this end fits the hex head. So the straight slot slips, this one doesn't. When it slips, you're taking a chance of jabbing that into your hand. Also, the either end on these screwdrivers have different size hex sockets. I don't have color-coded terminals, so what I'm going to use is color-coded wire for the ground and the hot. Ready to mount on the wall. Here's the relay that I purchased. It is a double pull and a double throw. 2 contacts, you can see right the top, right there. That's one of the contacts. The center part here is in contact with this end. That's normally closed. Then the bottom one, if you can see between these two, that's normally open. And then right here is a connection to the coil, and the other side right there, that's the other connection. So that goes to, these two are 110 volts. Now when this is energized, that'll pull down, and while it's energized, these two will be closed. We're not concerned with having this connected. What we're concerned with is the top one and the bottom one, the normally closed 2 contacts. these are going to be the ones that will energize the pump. So when we lose power, this will be in this position, closed, and the pump will be circulating. And what I'm going to do is connect these two sides in parallel with each other, and that should allow me to double my amperage that I'm using. I'm going to be running 4 pumps off of this relay. Right now I'm only running 2 pumps off of it. If you look real close, you can see the schematic diagram with the contacts and the switching on the printed on the surface, and it is the bottom view for these contacts, so it would be looking from the underside, which you can't see anything anyway. Before I wire everything up, I will use my meter and double check, verify that everything is going to be functioning properly. And right here you can see I've purchased a second set of relays. Always like to have a backup for any of the systems, so if something fails, I'll have that part right there ready to go. And the relay plugs into its socket. Okay, I'm going to use the ohm meter. Here I'm verifying that it reads. It should say 0, it's saying 0.002. Okay, that's basically 0 for us. Okay, now the coil, 110 volt, that's these two. We want to try to see which ones are connected, and it looks like number 13 and 14, and right here is 13 and 14. 9 and 1 are normally closed right there. When I turn the power on, it's open. That's how we want it to work. Now this is opposite of what the drawing is on the relay. So it says that 9 and 1 is normally closed. So you can't go by what's printed. So it's one good reason why to test everything before you go and put it in. And the contacts that I'm not using, I covered with tape, just so that there's no mistake when I'm hooking it up. Let me show what I have hooked up here. Okay, the bucket that I'm using, this is for the cyclone. You see I have the 3/4 inch vinyl tubing, and the center of the bucket I have it drilled with a fitting. Bottom of the fitting has the L pipe, and I have 3 foot of vinyl hose, and the rule pump is at the bottom. This will extend into the water about 1 foot, and the wire, the terminal, should be dry. It'll be coming out of the pipe. I'll have it zip tied right to the hose. Here's the installation, and what I'm going to do is unplug the unit. Unit's over there. There's the terminal strip and the relay, and you can see the light is on, meaning we have 110 volts. Now I'm reaching to the plug, unplugging, and I can hear running. So this would be the same scenario if we lost power. So the water's coming in, and you can see the cyclone action. And there's the drain. And it's overflowing. You can see right there, I increased the hole size. I kept cutting a little bit at a time until I got the size where the hole will allow all the water coming in to drain. So I'm using the hose without a restrictor. We don't need to have that. And I eliminated the elbow at the bottom of the tank. And let me turn it on. What it does different, here we're going to lose our power. Relay's turning on. See it coming in full force. And it'll slowly come up and it'll hang just right below the input of the pipe. And the way it's coming out at the bottom, it's coming out as a flare, which that is real nice also. Still coming up slowly. And again, this is the emergency aeration backup. So it may only have to run, well, last time I had a power outage it was 5 hours and I lost over 200 fish. So this has to be into the tanks. And that, from what I've been seeing, will put more air into the water than what the bubblers that I'm using are doing. Right there is at its maximum height. You can see here where the water's coming in, and it doesn't come up any higher. And when you disrupt it, it will start all over again. So I'm real happy with this system. And then the battery, let me show what's going on over here. I have the battery being trickle charged. So that's what's happening up here. A real small trickle charger. So that should maintain the battery full charge until we have a power outage. Yeah, I'm real excited with how this is working. I'll have one of these over each of the tanks. And that one relay will carry enough power to switch all the pumps on.
Thanks for watching, my friends. Bye-bye.